Our next topic is electrochemistry. So this intro video will give us some definitions, some units, and a little bit of setup to get going in the right direction. So when we talk about electrochemistry, we're talking about the study of the interchange of chemical and electrical energy. That's probably not surprising, so don't worry, we'll get into all of the details to help this make sense. This is really cool, and you'll see how it's related when we get later in this topic, but this is one way of using any of that free energy we happen to have available. So we will look at how electrochemical setups are related to delta G by the end of this section. Okay, so I'm going to do some units and measurements first. I actually don't have a lot to include in this section, and a lot of it you have likely seen before, or it is about to show up in physics. Although, for the life of me, I can never remember which semester you do electricity and magnetism in. And I will always forget, no matter how many times people tell me. But the two measurements and units that we need, the first one is amps, and we use a capital A for this. And amps is actually short for amperes. And so this measurement is the rate of electron flow through a wire. So if it is a rate, you should expect a time unit to show up in here. And you do see that. If you're just looking at 1 amp, it's kind of hidden. But if we break this down, an amp is actually a coulomb, which is, remember, the charge unit that we use for charge on electrons per second. So 1 amp is a coulomb per second, and it is also 1 coulomb is the charge of 6.242 times 10 to the 18 electrons. So 1 amp is 6.242 times 10 to the 18 electrons per second. The next unit that we need is volts, which we get a capital V for volts. This is a potential difference, and it is a potential energy difference. We'll kind of put the energy in parentheses here. So officially, I guess just in a few more words, let's make that a semicolon. It's the measure of the difference in potential energy per unit of charge. So 1 volt, well, a potential energy unit, we need some kind of energy unit, so something like joules perhaps, and it's per unit of charge. Well, coulombs is our unit of charge, so volt is the same as a joule per coulomb, and it is also referred to as EMF, which stands for electromotive force. So if you see EMF indicated anywhere, it just means the same thing as the potential difference or as volts. So there are 2 types of electrochemical cells that we are going to look at. We will spend most of our time on the first one. So the first type is a galvanic cell. And it is an electrochemical cell in which a spontaneous reaction occurs. And the other type of cell is an electrolytic cell, which hopefully from how we have defined galvanic cell, you can figure out what this is. But this is a cell where voltage is applied to push electrons and drive a non-spontaneous reaction. So we have a non-spontaneous reaction, but we're going to put some energy into that, push these electrons that need to flow to actually be the process of the reaction. And this energy is what's going to be used to drive that non-spontaneous process. All right, so I'm going to draw a picture of, I have it labeled as a galvanic cell. This will work for any type of cell, actually, although we tend to find with electrolytic cells, the setup is a bit different. But our definition is just that for a galvanic cell, it's spontaneous, an electrolytic cell is non-spontaneous. So we'll just call this electrochemical cell setup. And what we have two compartments. And for our picture, those are going to be a couple of beakers. So we'll do just a very terrible drawing of a beaker, and then get another one next to it. Oh yeah, that's really bad. That's fine. I will never judge your art skills because you always have to see what mine look like. The two compartments, one of them is the anode, one of them is the cathode. You will get definitions of what each of these mean in a later video, or actually later in this video. But it technically doesn't matter which you draw where, but by convention, the pictures that you will see me draw and a lot of the pictures that you will see in whichever textbook you're referencing will have the anode on the left and the cathode on the right. Now, left and right, like I said, doesn't technically matter. What is happening inside the cell is what matters, but we're going to get to that in a bit. Each one of these will have a solution. So let's get a solution and an electrode. So one solution in each, one electrode in each, and these are required components. So we have solutions. The electrode, it's usually just kind of a flat piece of metal, and we'll kind of color this in so you see that it's solid, and put a flat piece of metal over here. So there will also be some kind of external circuit which is just a wire with a meter. So if these are just little pieces of metal, it'll be a wire kind of with the little alligator clips, like the ones they use at the dentist, clipped on here, and then the wire is going to go and connect with another alligator clip to this other electrode in the other solution. So you'll have some kind of meter in here. I'm not going to label it as a voltmeter or an ammeter because I have this connected in series, and I know one of them needs to be connected in parallel, and I don't need you to remember that much for this. Just that this is how we get the information out. We'll have some meter that is connected to these wires in a way that will give us the information that we're looking for out of our cell as it's running. All right, and then we have something called a salt bridge, which is this kind of U-shaped piece of glassware that is stuffed with an ion solution that is going to help balance this reaction as it's happening. All right, so in terms of the components that we have going on here, the solution on the anode side will be something like a metal with some kind of plus charge and its counter ion. And then this electrode is made out of metal. The metal on the anode side is going to give up electrons, right? So from this metal piece, it'll give up an electron. It'll go into solution to become the M+. And these electrons are going to travel through the wire over to the cathode side. And this is some other metal, so I'm just going to call it M'. And in solution, my M' plus will be able to come up to this electrode, pick up an electron, and deposit on the surface. So this also needs some kind of counter ion. I've just written it as A-. It could be the same as the other flask. It could be different. It doesn't matter because it's just there to balance everything out. And then let me just write a few more words about the salt bridge. The salt bridge allows ions to move to balance charges. So if you have balanced redox reactions before, you have an idea of what this means. If you haven't, that is going to be an upcoming video. So you'll see why we need to balance the charges. It's not a solution in here. It's this kind of gel type stuff, and the ions all stay inside the salt bridge but move to the sides where they need to have the appropriate charges put. Okay, so this is a lot going on. If you wanted to tell someone about a galvanic cell, let's just say it's galvanic, that you had, that you were running, that you wanted to put together, communicating it through this drawing would take a really long time, and it's kind of a pain. So we do have a shorthand